and we'll be getting started today. Okay, so we last left off discussing exergonic and endergonic reactions and modeling and looking at the transition state and whether the transition state resembles the reactants or the products. Now, there's one other species that we need to talk about that can appear in a reaction mechanism or a reaction coordinate. And this occurs when we have a reaction that occurs in more than one step. So if a reaction occurs in more than one step, it must involve species that are neither the reactant nor the final product. These species are known as reaction intermediates or simply intermediates. Commonly, intermediates can be carbocations or carbon-centered anions. So for example, in the following addition reaction, we have our rate limiting step, which is attack of the alkene on the proton to generate a carbocation, intermediate. So this first species generated after the first step is our intermediate. Followed by a second step where we have attack of the carbocation to generate our final product. Now, what's really important to keep in mind is that for multi-step reactions, you need to be really careful to identify your rate limiting step. And as we discussed last time, the rate limiting step is the step with the largest activation energy. So this first step is rate limiting because this first step has the largest activation energy and the largest activation barrier. So this rate limiting step serves not only to control the overall rate of reaction, but can heavily influence product selectivity. Okay, so intermediates are neither reactants nor products. They're species generated as part of a multi-step reaction in the process of converting between reactants and products. Now, the intermediate will, in this case, the intermediate often and the transition state will resemble one another. In this case in particular, we're looking at an endergonic reaction. So in this following reaction, our intermediate and transition state will often resemble each other. It's important to note that each step has its own free energy of activation, and your complete reaction coordinate shows the free energy changes associated with each intermediate and each reactant and product. Okay, perfect. So just as a general rule, when we're looking at and we're analyzing reactions, first thing we have to do is to classify whether the reaction is exergonic and endergonic. And you're going to repeat this process for each step. Now, focusing in on the rate limiting or rate determining step, we're going to look and see, based on whether the reaction step is exergonic or endergonic, we can conclude and we can estimate what species the transition state most resembles. So if the reaction is exergonic, we can estimate the relative energy of the transition states by looking at the relative energies of the reaction products. The transition state structures will be similar to our products. If the reaction happens to be endergonic, we can estimate the relative energy of our transition states by looking at the relative energies of the reactants and drawing our transition state structures relative to the reactants. Okay, so let's try to put this into practice. And let's look at the following example. So in general, the faster reaction has a lower activation energy. And the activation energy depends on the difference in energy between the transition state and the reactant energies, okay? So we have two different activation energies, and the activation energy is directly dependent on our transition states. So this is our first activation energy, and then we have our second activation energy. Okay. So in this case, so starting our analysis from scratch, is this overall first step endergonic or exergonic? Is this overall first step endergonic or exergonic? What does everyone think? Looking at this first step in our reaction mechanism, is it endergonic or exergonic? And don't be shy to share your responses in the chat or verbally. So we have students proposing that it is endergonic. That's exactly right. This first step is endergonic because our overall Gibbs energy change for this first step is greater than 0. Okay, so this is an endergonic step. Okay, so endergonic steps in turn, if we look at which species reactants or products is closer in energy to our transition state, we notice that our transition state is closest in energy to our products, so then our transition state will resemble our products. So we can use the relative energies of our products to estimate the relative energies of our transition state. So endergonic transition state resembles products. Okay, so in the following case, as we notice, our reactant energies are identical for these two possible products. We're starting from the same reactant. However, the two products have slightly different energies. And as we notice, if we are comparing a primary versus a tertiary carbocation, which carbocation would we expect to be lower in energy? If we compare primary versus tertiary, which carbocation intuitively would we expect to be lower in energy, more stable? Exactly right. The tertiary carbocation is lower in energy. So in this reaction pathway, we have the same reactant that can undergo two different pathways to generate two unique products. This reaction is endergonic, and as a result, our transition state will resemble our products. So in turn then, for this endergonic reaction, the reaction that generates the lower energy product in turn will have a lower energy transition state that resembles those products. And since the transition state is lower in energy, in turn, the activation energy would be lower. Thus, for an endergonic reaction, in this case, this reaction, the reaction that produces the more stable carbocation occurs at a faster rate, favoring the tertiary carbocation product. So let's unpack this one more time. So we have the same reactant, two unique products. We've analyzed our products and we noted that the tertiary carbocation is lower in energy. That's the first thing that we need to know. Okay. Next, because this reaction is endergonic, the transition state will resemble our products. And as a result, the energy of our transition state, the relative energy of our transition state, closely matches the relative energies of our products. Since the tertiary carbocation product is lower in energy, the following transition state to make that tertiary carbocation would be lower in energy, and as a result, because the activation energy for this green reaction pathway is lower, this green reaction pathway is preferred, and the tertiary carbocation intermediate is preferentially formed. Does that idea make sense to everyone? Does that argument make sense? So key takeaway, endergonic reactions, the transition state resembles products. And it's really easy to see that because the products are closest in energy to our transition state. Okay, so let's keep going now and let's look at a case study where we're comparing endergonic and exergonic reactions. So a classic reaction is radical bromination and radical chlorination. So this radical reaction can be broken down into a series of initiation, propagation, and termination steps. And at the end of the process, we've in effect replaced a hydrogen with a chlorine atom. This reaction occurs through a radical mechanism, and we can break down this radical mechanism into a series of discrete steps. Okay, so that's what we're looking at right now. Now, if we think a little bit about the selectivity for radical chlorination versus radical bromination, if we just look at the total number of hydrogens, comparing the primary and the secondary position, we see we have 6 primary hydrogens and 2 secondary hydrogens. So we would expect a 3-to-1 ratio. We'd ideally expect a 3-to-1 ratio of primary to secondary if we were just grabbing hydrogens at random. Statistically, you're more likely to abstract a primary hydrogen. However, in reality, what we observe is that the secondary hydrogens are substantially more reactive. And we can estimate this selectivity factor by comparing our estimated probability of reaction to the actual observed reaction ratio. So as we notice, accounting for the number of hydrogens present that are primary and secondary, we notice that the secondary hydrogen is roughly 3.7 times more reactive towards chlorination compared to the primary hydrogen. Okay, that's why we observe this somewhat dramatic difference between our statistical prediction and the actual ratio of primary versus secondary chlorination. Does that make sense to everyone? Does everyone notice how the secondary position is substantially more reactive compared to what we'd expect from a statistical pattern of reactivity? Does that idea make sense? Is everyone comfortable with this concept so far? Any questions so far? So for chlorination, we observe slight selectivity for the secondary positions. That makes sense intuitively because if this is a radical mechanism, we know that secondary radicals are preferred over primary. Now, where we really begin to see something interesting is that if we look at the selectivity for radical bromination is in general considered substantially more selective than chlorination, with the only caveat being you get substantially less reactivity. If we compare our statistical to our actual mixture, we notice that in our actual product distribution from radical bromination, our secondary product is heavily preferred. Now, Although these two reactions are going through very similar mechanisms on paper, it's important that we look at the reaction coordinate, because from the reaction coordinate, we can be able to explain why radical bromination is so much more selective. Does that overview make sense? Does everyone understand what we're looking at and what we're trying to explain in this case study? So we're going to utilize what we've learned about reaction coordinates and modeling transition states for different reactions in order to explain why is radical bromination so much more selective, and what are some drawbacks of radical bromination and what are some benefits. Does that make sense to everyone? Okay, so let's just provide some background. We know that secondary radicals are more stable than primary radicals. So this preference for selectivity for chlorination and bromination at the secondary carbon makes sense at a superficial level, right? That makes sense from a broad view perspective. This is a radical mechanism. We are likely proceeding through a radical intermediate, and the stability of that radical intermediate likely impacts our product distribution. That's why we see a preference for the secondary bromination or chlorination. That explanation alone does not explain why bromination is abnormally selective. It has an abnormally high selectivity. So, if we think about the energetics for this reaction, the selectivity determining step or the rate determining step for this radical bromination or chlorination is radical formation after hydrogen abstraction. Okay, so in this case, we're comparing a primary versus a tertiary position, and we're comparing bromination versus chlorination. Now, I want you to pay special attention to these energy values, and I'd like you to tell me, do you notice anything a little bit odd? Do you notice anything a little bit different about the enthalpies associated with this radical abstraction step for chlorination versus bromination? Actually, to make this really easy to see, looking at this first reaction, looking at the first set of reactions involving radical abstraction in chlorination, would we consider these steps exothermic or endothermic? Would we consider these steps approximately exergonic or endergonic, these first steps? These first steps would be considered exothermic and likely exergonic. Okay, so we can likely estimate from these enthalpies that our Gibbs energy of reaction is going to be less than 0. Okay, if we look at bromination, are these steps endothermic or endergonic, or are these exothermic, exergonic? For bromination, it's endergonic, exactly right. Okay, so we have our critical distinction. Now, this may not seem like a big deal, but does this make a huge difference when it comes to our transition state? Does this observation make a pretty big difference when it comes to our transition state? Yep, exactly right. It does. Because remember, exergonic reactions resemble the reactants. Endergonic reactions resemble our products. Okay. So, because the hydrogen abstraction step for chlorination is exergonic, the transition state resembles the alkane and chlorine atom. So if we think about our transition state, if we think about our transition states for these two possible steps, we'll see a diagram of this momentarily. The transition state resembles our reactants, and there is little radical character on the carbon in the transition state. So in turn, because our transition state resembles our reactants, the regioselectivity is only slightly influenced by radical stability. So to put this another way, as chlorination is exergonic, the transition state resembles the reactants, and we use our reactants to estimate the energy of our transition states. Now, as our transition states resembles our reactants that are close in energy, the transition states in turn are close in energy, and there's a small difference in activation energy for both reaction pathways. And because there's a small difference between these two pathways, chlorination has relatively low selectivity despite the difference in product energies. So we have our reactants, right? So we have our reactants. And if we look at our transition state resembles our reactants. Now, because our transition state resembles our reactants, we're primarily looking at an alkane and a chlorine-centered radical. And there is very little difference between the reactants if we compare the alkane reacting at the primary or tertiary position. The radical character doesn't play a huge role in the transition state energies, because our transition states are more closely resembling our alkane starting material. Because there's a small difference in the activation energy for these two pathways, so if we have our primary pathway and our tertiary pathway, even though the tertiary chlorination product is lower in energy, substantially lower in energy, we only see a very small amount of selectivity for the tertiary product. Does that idea make sense? Does that idea make sense and tie things together? Does that argument make sense to everyone? Perfect. So this is why chlorination is not particularly selective. Our transition state resembles our alkane starting material. There is very little difference in energy between the alkane reactant via the primary or tertiary reaction pathway, because it's the same starting material. And as a result, even though the tertiary product is substantially lower in energy, we don't often see an extreme selectivity for the tertiary product, because what determines selectivity is the activation energy and the difference in activation energy between our two pathways. Okay. Now, if we look at bromination, by contrast, the hydrogen abstraction for bromination is endergonic. Well, this entails a bit of a drawback in that we have to put a fair amount of energy in to get this radical abstraction to go. And the transition state in turn resembles our intermediate product. So the transition state resembles an alkyl radical, an HBr, and there's a significant amount of radical character on our carbon in our transition state. And as a result, our regioselectivity is influenced by radical stability, and we know that the tertiary position is preferred over the primary position if we're generating a radical. And just to continue on to really drive this point home, as bromination is endergonic, the alkyl radical energies can be used to estimate the transition state energies. And as the alkyl radicals that resemble our intermediates have substantially different energies, the transition states in turn must have different energies. Thus, bromination is more selective as the transition states have substantially different energies. So if we compare our tertiary pathway to our primary pathway, because our intermediates have a lot more radical character, the tertiary reaction pathway would have a substantially lower activation energy because the transition state resembles our tertiary radical product, and tertiary radicals are more stable than primary radicals. Does that argument make sense to everyone? Does that argument make sense? So this in turn explains why, even though bromination and chlorination are both going through radical mechanisms, whether the reaction is exergonic or endergonic has a huge effect in how we interpret and analyze the reaction and how we model our transition states. So this is a pretty interesting application of the Hammond postulate, and I feel like it helps and showcases the application of the Hammond postulate to both explain selectivity patterns and to explain differences between two possible reaction pathways. Does that make sense to everyone? Does this idea make sense to everyone? Okay, so what I want you to take away from this is not necessarily that bromination is more selective than chlorination. That's just sort of a random fact. What I do want you to be able to take away is, given a statement, given a pattern of reactivity, and given thermodynamic data, either a reaction coordinate, a comparison of the reactant or product energies, or some information about the reactants or products, or some information about the reaction mechanism, you should be able to draw one of these reaction coordinates and interpret and compare the transition states for these reaction coordinates. We are going to be doing this a lot in chapter 7 when we talk about substitution and elimination reactions. And we can talk about how different factors in our reaction can influence the transition state, reactant, and product energies, and in turn influence the overall activation energy for our reaction. So, any questions on the Hammond postulate? So you've seen examples of analyzing exergonic and endergonic reactions. Does that make sense to everyone? Does this postulate make sense in terms of how it functions and how it's utilized for analysis? Okay, so now what we're going to do is we're going to look at various general types of reactions. So this is an overview of different types of reactions or steps that you would see in reaction mechanisms. We're going to look at these different reaction steps and types of reactions at a broader level in this first look. And then in subsequent chapters, we're going to get more detailed in terms of the reaction mechanism, in terms of selectivity, and factors that influence the reaction. But for now, we're just going to focus on being able to draw and interpret different types of reactions. So, with that said, the first major type of reaction that we're looking at is an addition reaction, where two molecules will combine, typically involving an alkene or a ketone. Okay, so in electrophilic addition, a nucleophilic pi bond is used to form two new sigma bonds. So we have our pi bond, and in this case, an alkene is protonated by forming a carbon-hydrogen bond, then the carbocation is attacked by a nucleophile. So we have two distinct steps, protonation followed by attack. As we notice, our pi bond or our alkene is the nucleophile in the first step. It is donating and contributing the electron density used to form our first bond. Now, outside of the polar addition mechanism, there's also the radical addition mechanism, where a radical adds to a pi bond to form a set of new sigma bonds. The last type of addition reaction that we'll see is nucleophilic addition, where a nucleophile adds to an electrophilic pi bond to form two new sigma bonds. So in this case, our pi bond is functioning as our electrophile. Any questions on general types of addition reactions? These are very common superclasses of addition reactions that you'll see in reaction mechanisms. Any questions on these general types of reactions? Okay, let's keep going then. And let's try to apply our Hammond postulate for electrophilic hydrobromination of an alkene. Okay, so in this case, we're looking at our reaction that we've seen previously where we have our alkene. And in our first step, we protonate our alkene. And we generate a carbocation species. What do we call a species that is neither a reactant or a product? What do we call this species that is neither a reactant nor a product? What do we call that? An intermediate, exactly right. So we make a carbocation intermediate. That's shown right here. And then in our second step, our carbocation intermediate is attacked by our nucleophile to form our final carbon-bromine bond. Okay, so now what we're going to do is we're going to analyze this reaction coordinate. We're going to explain how this reaction coordinate was put together and sort of rationalize the selectivity for this reaction. So, first and foremost, we need to look at our two activation energies for our first and second steps. And I'd like you to tell me, which step is selectivity determining? What step is rate determining? Step 1 or step 2? Which step is rate determining? Which step has the highest activation energy? Step 1, exactly right. So we know step 1 is rate limiting, rate determining, and selectivity determining. Okay, so we're going to focus our analysis on step 1 because the rate determining step is the most important step in a chemical reaction in terms of product selectivity in most cases. Okay, so looking at the following reaction coordinate and looking at the first step. So is step 1, is this first step exergonic or endergonic? So if we compare the Gibbs energy of reaction for our first step, is our first step exergonic or endergonic? Endergonic, exactly right. So the first step is endergonic. Okay, so in turn, that means our transition state will resemble our quote-unquote product, which in this case is our carbocation intermediate. Okay, so because our transition state will resemble our carbocation intermediate, so we've identified the rate limiting step. That is going to be step number 1. We've identified that our reaction is endergonic. Okay, perfect. Now what we're going to do is we're going to look at two competing reaction pathways, and we are going to determine which of these reaction pathways is favored in this chemical reaction. So we're just looking at step number 1. We know that step number 1 is endergonic. And what I'd like you to do as a group problem solving example is I'd like you to consider these two competing pathways for hydrobromination. And I'd like you to match. So I'd like you to take a look and I'd like you to identify in this scheme which of these two products, A or B, corresponds to each of these two reaction pathways. And then I'd like you to identify the kinetic and thermodynamic product. And I'd like you to tell me which intermediate is preferred in this reaction pathway. So you may have to break out the annotate tool for this. And we'll discuss this example in about 3 to 4 minutes. So you're given two reaction pathways. I'd like you to match each intermediate to each of these reaction pathways. I'd like you to explain which intermediate is preferentially generated and why. So let's take about 3 to 4 minutes and then we'll discuss this example. And don't be shy to contribute your proposals in the chat and to use the annotate tool to match each of these reaction pathways to one of these two intermediates. And explain which of these intermediates is preferentially formed in this reaction. And don't be shy to share any questions and comments that you have in the chat or verbally. And we'll discuss this example in about another 2.5 minutes. So we have a proposal that this pathway in green would generate our intermediate B. And we have a student proposing in the chat that B is the kinetic product and the thermodynamic product. I'm going to put this in quotes since these are intermediates. Okay. Would you care to elaborate on your reasoning? Why did you select B as the intermediate generated from the lower energy pathway? What is unique about intermediate B compared to A? Would you be able to elaborate a little bit more of your logic? Would anyone else like to contribute some input into this discussion? So why do we think, so we assigned tentatively that The green reaction pathway will generate intermediate B. So we think intermediate B is generated as the quote-unquote kinetic product, as it has the faster rate of reaction. But let's try to delve into, why do we think that? What is our basis? Why do we think intermediate B, that pathway to make intermediate B, has a lower activation energy? What can we apply the Hammond postulate to explain or rationalize that argument? So we have some pathways and we're comparing the transition state energies. And yes, you've noted that the activation energy for the reaction pathway B is lower. That's correct. But let's try to get at why does reaction pathway B have a lower activation energy? What's unique? What can we invoke? What can we utilize to explain this idea? So if we were to think about this transition state, what would this transition state resemble? What would this transition state resemble in terms of structure and energy? What will this transition state resemble? Yeah, the transition state resembles our products, right? So if we compare our products A and B, which of these intermediate products is lower in energy? Yeah, so B is lower in energy. Exactly right. It's a tertiary carbocation. So we can in turn, let me circle this in green so that way it's consistent. Yes, exactly right. So as we've noted in the chat, intermediate B is lower in energy. And as a result, because this tertiary carbocation is lower in energy, what does that tell us about our transition state? If our quote unquote product B is lower in energy, in turn, that means the transition state for pathway B is lower in energy. Does that argument make sense to everyone? Does that argument make sense? So we looked at our two possible products. We said, okay, which of our two possible products is lower in energy? We noticed B is lower in energy. This is an endergonic reaction. Our transition state resembles our products. Since B is the lower energy product, the transition state for B will be lower in energy. And because of that, the activation barrier for pathway B is lower. And in turn, pathway B or product B would be the kinetic product. It's not just the kinetic product, it's also the thermodynamic product, because product B is also the lowest energy product. Does that argument make sense? So make sure that when you go to assign a reaction pathway, make sure you consider whether or not the reaction is exergonic or endergonic, and then make sure to carefully consider in turn, what does my transition state look like and how does that impact my activation energy? Does this example make sense to everyone? Does this type of analysis make sense to everyone? Any questions on this analysis? Okay, so let's keep going now. So if we were looking at these two reaction pathways, so if we're comparing pathway B and pathway A, in our diagram, we looked at our two different pathways and we considered that our first step is selectivity determining and our first step is rate determining. By looking at our two steps, we notice that our tertiary carbocation is lower in energy, and because this reaction pathway is endergonic, the transition state resembles our products. The lower energy product has the lowest energy transition state, and in turn, the lower in energy our transition state, because we have the same reactant, the faster reaction and the preferred reaction will have the lowest energy transition state. So we concluded that this addition reaction favors addition of our bromine at the tertiary position because the tertiary carbocation is preferentially generated as an intermediate. Okay, so from applying the Hammond postulate, we're able to understand in detail the regioselectivity for these addition reactions. Okay. So let's work now on drawing out these different addition reaction mechanisms using arrow pushing notation. So let's practice looking at each of these different types of addition reactions, and let's focus on drawing out these mechanisms using arrow pushing notation. So if we were trying to showcase nucleophilic addition, how would we draw our arrows in arrow pushing notation? So if we are forming a new sigma bond and breaking a pi bond, how would we draw this process using arrow pushing notation? Would someone like to try with the annotate tool, drawing out an arrow pushing mechanism for this reaction? Would anyone like to propose, given what we've seen for these nucleophilic addition reactions, would someone like to try drawing out an arrow pushing mechanism for the following reaction? Okay, so we have our first arrow drawn. And as we form that new bond, what happens to our double bond? Yep, exactly right. Exactly right. Perfect. So for this nucleophilic addition, we draw the attack towards our electrophilic carbon, and we break our pi bond to generate a lone pair on oxygen. Perfect. Exactly right. Now let's try to draw arrow pushing notations for the radical addition reaction. So in radical addition, remember to show one electron motions, we have to use a fishhook arrow. So would someone like to attempt drawing the mechanism or drawing the first step for this radical addition reaction? And don't be shy to use the annotate tool to draw out this first mechanism for this radical addition reaction. And we're on the right track. The fishhook arrows show the movement of one electron. Considering that this bond has 2 electrons, where is that other electron coming from? So we have 2 electrons in our double bond. So how do we form this new single bond? We need to draw one more arrow to complete this. Yep, exactly right. Exactly right. Perfect. Perfect. So to summarize, for radical addition, we have a 1 electron attack of our radical. The alkene contributes an electron to form our first single bond, and we end up with a tertiary radical. As we've discussed previously in our discussion of the bromination versus chlorination selectivity, in general, it's preferred to generate the tertiary radical in this case. Does this mechanism make sense to everyone? Does this pattern of arrow pushing make sense to everyone? Part of what we're doing in this section is getting people used to common energy diagrams for these different reactions and getting used to drawing out different general reaction mechanisms using arrow pushing notation. It's just getting used to these mechanics involved in drawing out reaction mechanisms. Does that make sense to everyone so far? Is everyone comfortable with this idea so far? And don't be shy to break out the annotate tool and try to contribute your perspective. So now we're looking at electrophilic addition. We've seen electrophilic addition before. It's a 2-step reaction mechanism. Remember, when we did our analysis of electrophilic addition, we looked at both steps individually. Would someone like to draw the first step and our first intermediate for this mechanism? Would anyone like to try drawing the first step and the first intermediate? You can utilize the annotate tool, or you can share your responses as a picture in the chat, and I'd be happy to take a look and provide feedback. Would anyone like to try drawing the first step for this reaction mechanism? So we're looking at electrophilic addition. So what would be our first step in electrophilic addition? And remember, we've seen this reaction in detail when we looked at its reaction coordinate diagram earlier on today. So what is our intermediate species in this reaction? To help us guide our discussion, what's our intermediate species generated in this reaction? So you have the right general idea. The only difference is rather than forming a carbon-centered anion, our alkene attacks our electrophilic hydrogen and we generate a carbocation. Now, if we have a preference, would we rather make a tertiary or a secondary carbocation? If we had a preference, would we rather generate a tertiary or a secondary carbocation? Tertiary, yep. So we generate our tertiary carbocation and we have our carbon-hydrogen bond. Now, since we have a nucleophile floating around, to form our carbon-bromine bond, we simply attack our carbocation. Well, in this case, we have chloride floating around, so we simply attack our carbocation. And as we discussed previously, this first step is our rate limiting or selectivity determining step. Is everyone comfortable so far with these different general mechanisms and drawing out each of these general mechanisms using arrow pushing notation? We're just helping students recognize general patterns so that way when we encounter more detailed mechanisms in later chapters, we can efficiently and comfortably draw those mechanisms. Okay, so let's discuss some common bond forming and bond breaking mechanisms. So in homolytic cleavage, we have symmetrical bond breaking, where electrons in the bond are evenly distributed to the two atoms as the bond is broken. So for example, if you have a chlorine-chlorine bond, in homolytic cleavage, each of our chlorine atoms gets one electron from the bond. For polar reaction mechanisms, we have polar addition, where our two bonding electrons are donated by one reactant. Likewise, we can also break bonds in a heterolytic manner called heterolytic bond cleavage, where the electrons shared between the two atoms in our bond are distributed to one atom during the bond breaking event. In terms of radical bond formation, this is primarily encountered in termination steps where two radicals react to generate a stable product. So these are the common radical and polar bond forming and bond breaking steps that you'll see in many common mechanisms. Do these steps look familiar for everyone? We discussed them at the beginning of the chapter, but I wanted to make sure we reviewed them just so because we're going to be drawing a lot of mechanisms in later chapters, and I want to make sure that people are comfortable with these basic bond forming and breaking steps and drawing these steps. Does this make sense to everyone? Perfect. Okay. So we've looked at some bond forming or addition reactions. Let's look at some typical elimination reactions. So there are two general types of elimination reactions that we'll see very commonly. The first, elimination generally, is the formation of a pi bond by breaking one or more sigma bonds through the loss of a leaving group. The two major types of elimination reactions that we'll see in this class are the E1 and E2 reaction. In the E1 reaction, we end up with loss of our leaving group to make a cation, followed by elimination of H+ to yield a pi bond. So it's a stepwise reaction mechanism. In the E2 reaction, we have a concerted loss of the leaving group and hydrogen to generate an alkene. The last type of elimination reaction that we'll see quite commonly is 1,2 elimination, which involves the loss of a leaving group to reform a carbon-nitrogen or carbon-oxygen pi bond. So these are the three general classes of elimination reaction that you'll see a lot in this course. Now, the last major type of elimination that we'll see is known as E1CB, which involves deprotonation of an acidic proton followed by elimination of our leaving group. So the E1CB is facilitated under basic conditions, where first we deprotonate and then we eliminate. So another example of this would be if you have this beta halogen and you have an acidic proton, your base would remove the proton. Once you have your anion, you then eliminate your halogen to form your desired pi bond. Do these general mechanisms make sense to everyone so far? We'll be looking again at each of these reactions in detail in later chapters. I just want to expose you in this chapter to the general arrow pushing patterns that we'll see and the general characteristics of each of these reactions. Does this make sense to everyone so far? Okay, now the E1CB can also occur through, and this elimination process can occur through conjugated system. So you can kick your electron density through your conjugated system and eliminate your halogen through an exactly similar mechanism to our typical E1CB reaction. Okay, so now that we've seen some common reaction mechanism types, let's practice drawing arrow pushing notation for each of these mechanisms. So I'd like us to work on trying to draw the mechanism for 1,2 elimination of the cyanide anion. So let's take about 2 to 3 minutes and try to use the annotate tool to draw the arrow pushing mechanism for this following reaction. So we know that this is a 1,2 elimination. Now all we have to do is draw the arrow pushing mechanism. So that way we can generate the desired bonds and break the bonds needed to generate our products. So don't be shy to break out the annotate tool or to try drawing out your mechanism on paper and sharing your proposed mechanism as a picture in the chat. And we'll discuss this example in about 2 to 3 minutes. I really want students to start trying to draw a reaction mechanism for each of these different types of reactions. So that way we can get a little bit more used to the mechanics behind drawing mechanisms. So would anyone like to try using the annotate tool to propose a mechanism for the following reaction, which is a typical 1-2 elimination? Let's give everyone a little bit more time to work through this problem and to try to propose a mechanism for this reaction and showcase this step using arrow pushing notation. And we'll discuss in another minute to a minute and a half. Yep, exactly right. In 1-2 elimination, we kick our electron density down and our leaving group in turn leaves. Exactly right. So in this mechanism, for 1-2 elimination, our lone pair is kicked down to form our pi bond, and our leaving group leaves to generate our leaving group anion. Does this example make sense to everyone? Does anyone have a question on this 1-2 elimination mechanism? Let's look at another very common step in many reactions, which involves the elimination of water. So I'd like you to attempt to draw a mechanism for the following elimination reaction. This is a polar reaction mechanism. Or a polar step. So let's give everyone about 2 to 3 minutes to try to draw a mechanism for the following elimination reaction. And don't be shy to share your questions or your responses in the chat or verbally or on the class whiteboard using the annotate tool. So let's work through this example and let's try to draw a mechanism for the following elimination reaction. And to give everyone multiple spaces to draw, let me redraw the same structure down here, just so that way if multiple students want to comment, they can both share their responses. So I see both students have proposed the same general arrow pushing trend, and that's great to see. So let's summarize the student responses. So in this elimination, our lone pair is kicked down to form our pi bond, and our leaving group leaves. You can draw this as a concerted process, and in this case, it wouldn't be particularly unreasonable to draw it as stepwise either. Perfect. Okay, so let's continue to practice. Let's continue to practice drawing out some elimination, addition, and substitution reactions. So let's look at the following reaction where we're dealing with dehydration and elimination of water via an E1 process. And remember, the E1 process can be broken into 2 steps. Would someone like to try drawing the first or second step for this reaction? And to make things easier, you can abbreviate the base as just a B with a lone pair. So would someone like to try to draw out the mechanism for the following E1 process? And remember, when we think E1, we go through a carbocation intermediate. So let's work on this example for about 2 to 3 minutes, and let's try to draw the mechanism for this elimination reaction. So we know the E1 process involves generation of a carbocation followed by elimination. So we have our first step. And what would our intermediate look like then? What would our intermediate look like then? Perfect, perfect. So just to draw that first step out, so we have our leaving group. So let me just to make it easier for the annotations to be added. So our leaving group leaves, and we're left with our carbocation intermediate. That's exactly right. And now what would the follow-up step be? Once we've made our carbocation intermediate, what happens? What is our second step? Let's try to contribute responses for the second step using the annotate tool. And it's great to see that we're working our way through these different general mechanisms. Would anyone have a proposal for the second step of this reaction? So once we have our carbocation, how do we generate our alkene? How do we generate this elimination product? So let's keep working on this example, and don't be shy to share your proposed responses using the annotate tool. Would anyone like to propose the second step for this mechanism? The student contributions were great for the first step. Let's try to finish off this mechanism by drawing the arrow pushing mechanism for this second step. So to help provide some clarity, it's great that we got the first step. In our second step, our base abstracts our proton and we eliminate to generate our alkene. So in the second step, we remove our proton with our base, and then the electrons in this carbon-hydrogen bond are used to generate our alkene. Does this make sense to everyone? Did that clarify any confusion that students had when they were working through this mechanism? Does this make sense to everyone so far? Perfect. So let's try to draw another mechanism. This time we're looking at elimination via an E2 process. So I drew out the proton that we're going to be eliminating just to make it easier to see. and I'd like someone to try to contribute the arrow pushing mechanism for the following E2 reaction. So let's take, again, about another 1.5 to 2 minutes, and let's try to draw an arrow pushing mechanism for the following reaction. And don't be shy to share your proposed mechanism using the annotate tool or by proposing a picture of your drawn mechanism in the chat. Okay, we have one of our arrows drawn. Okay, so we have our base abstracting our proton, and then in turn, what happens to the electrons in our carbon-hydrogen bond? How are we making our double bond? How are we making our pi bond then? You're almost there. You just need one more reaction arrow. You just need one more. Yep, exactly right. So just to clarify, the way that you've drawn the arrows looks reasonable. So we have our base. So to be more specific in this case, our base in this case is tert butoxide. So our base abstracts a proton. The electron density in our carbon-hydrogen bond is used to form our alkene, and our leaving group leaves. Perfect. It's great to see students contributing as we work through each of these different mechanisms. Okay, so this is a good stopping point for today. So we're going to take a quick 10-minute